Hello again. This is Space Nuts Q&A, where we talk astronomy and space science. Although in this edition, it's all about what the people want to know, questions from our audience. And today, we'll be talking about that old chestnut radio interference. We've got a question that asks about the viability of a universe. How small is too small for a universe not to actually be viable? Dark matter and angular momentum and things like that, and water behaviour. We know how it behaves on Earth, but what about other places? Is it different? That's all coming up on Space Nuts Q&A.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
He's back again. Professor Fred Watson, astronomer at large. Hi there, Fred.
You can't keep me away, Andrew. Here I am, ready and willing as always.
Excellent. All right. Well, we might as well just dive right on in. We've got a few text questions today and one audio question. Our first question comes from Tobias. He said, "G'day, Space Nuts, you legends." We're legends, Fred. Is Tobias saying we're old? Yeah, that's what it is.
I'll take legends. I'll take it.
He says, long-time listener, literally have listened since day one to today. That's fantastic. Thank you, Tobias. Don't know how we kept you, but it's good. It's good. We managed. He said, first-time questioner, though. I live in Marsfield in Sydney, right next to the CSIRO astrophysics lab where Wi-Fi was invented. Wow. Has Professor Fred ever been to the site? And maybe, if you have, what did you do there? I've noticed that the radio telescope on the facility has not moved in a long time. Does radio astronomy still take place there, or is it just a research facility? Would interference from terrestrial radio interference make radio astronomy at this location a waste of time? Secondly, I've noticed in a lot of areas around Sydney and presumably in most towns and cities around the world that the old school orange, yellow, high-pressure sodium streetlights are being replaced with much more efficient LED lights. Is Professor Fred able to say if this is making astronomical observations better or worse? If the same light was replaced from a high-pressure sodium light to LED, and they're putting them in the same, putting out the same lumens in the colour wavelength of light, is the colour wavelength of light going to make a difference to astronomical viewing or seeing? You guys are legends, and your podcast is the best of all on the internet. Thank you so much, Tobias in Marsfield. Oh, that's lovely, Tobias. Thank you. He doesn't listen to any others, but no, it's nice to get some feedback. Appreciate it.
And I'm very happy to have a go at Tobias's questions as well, of which there are several. So let's go through them because I've got questions in front of me too. Have I ever been to the CSIRO astrophysics laboratory at Marsfield? Well, actually, I used to work there, not in the astrophysics laboratory, but in the same site, the headquarters of what was the Anglo-Australian Observatory and then became the Australian Astronomical Observatory. That's where they were. That was our Sydney headquarters, laboratories, workshops, offices, and that's where the telescopes at Coonabarabran were operated from. So my job was the astronomer in charge at Coonabarabran, but I spent a lot of time also at the Marsfield site. The radio telescopes there are some radio telescopes, and yes, they are not state-of-the-art any longer, so they're probably ornaments rather than being used. There might be some tests done on them because you still often need to take tests, images, or just check out amplifiers and things of that sort from there. Yes, I should say the site is the home of CAS. CAS stands for CSIRO Astrophysics and Space Science. So that's the name of it. It used to be the Astrophysics Laboratory, but it's now CAS. Radiophysics Laboratory. It's now CAS. So, yes, the reason why we don't do frontline radio astronomy from there is exactly as Tobias says, too much radio interference mobile phones, microwaves, telecommunications, everything around there, spoiling the view of the sky. And then he moves on to something that's closer to my expertise, because I had a great deal to do with this when I was astronomer in charge, about the high-pressure sodium lights, the orange-yellow ones. They're actually slightly pinkish at high pressure. The orange-yellow are the low-pressure ones. Pink, they are yellowish, but they move towards pink almost to the high-pressure ones. They are being replaced by LEDs. Does it make observations better or worse? Well, okay. It's all about what it contributes to light pollution. And Tobias's question, if the same light was replaced from a high-pressure sodium light to an LED light, and they're putting out the same lumens, that's the intensity of the light, is the wavelength or color going to make a difference to the astronomical seeing? And the answer is yes, because generally the LEDs are a much whiter light. We describe it in terms of something called color temperature. And a color temperature of 5,500 degrees Kelvin is the same color as the sun, as sunlight. And that's an intense white. So LEDs are, for various reasons, they've tended to be this intense white. We see them in car headlights. It's actually quite damaging in the sense that scatters through the atmosphere much more readily than the warmer colours of the sodium lights, which have a colour temperature of around about 2,700. So less than, kind of half what some of the LEDs do. And that does make a difference. On the other hand, there is a positive for LEDs, which is that they are much more controllable. You can send the light down much more easily than you can with sodium lamps. So it swings and roundabouts, basically. But great questions. Thanks very much, Tobias.
Yes, indeed. And of course, we see a lot of towns and cities that are taking on board the Dark Sky project that you and Marnie have been involved in, particularly Marnie, and trying to direct that light downwards. Certainly here, we talked very recently about radio interference that's potentially going to affect the likes of the square kilometre array, but that's more to do with satellite coverage. But I suppose it's a bit sad, but not surprising that those radio telescopes at Marsfield have been rendered useless by being right in the middle of Sydney, where all those mobile phone towers and mobile phone signals are that pretty well kill it. But it's very exciting, Tobias, to hear from you and learn that you live next door to the place where Wi-Fi was invented. I just wondered, do you get free Wi-Fi as a consequence of that? Get a bit of a sneaky overflow, maybe. But that's a lovely to hear from you after so very long. Wow. And thanks for the question. Let's move on to our next question. You recently had a question about black holes creating other big bangs. If we live in a multiverse, how small could a universe be to remain viable? The size of a galaxy cluster, a single galaxy, or even a single solar system? Thank you for all your awesome episodes, from Jeffrey. Look, let's assume for a moment there are multiverses, and there's certainly evidence starting to build that suggests that may be the case. It certainly has not been written off. But how small is too small for a universe to be a viable universe? I love this question, Fred.
Yes, it's a great question, and I don't know the answer. I think if you have a universe created within a Big Bang, this is basically Roger Penrose's theory, and that might be the place to find answers to this, Jeffrey, if you feel like hunting it out on the web. Although everything that Penrose does tends to be highly mathematical, because that's what he is. He's a mathematician with a Nobel Prize as well. Yeah. So if you think of a Big Bang that spawns another universe, it will be highly compressed, as ours was at the time of the Big Bang. It was basically a singularity with density approaching infinity, and everything, matter, space, everything compressed into a very small space. So I don't know the answer to the question whether a Penrose type multiverse evolution would allow for different sized universes. I simply don't know the answer to that. I suspect not. I suspect universes tend to be not necessarily come in one size, but, tend to be big rather than the kinds of things that I think Jeffrey is thinking of. It's a great question, though, and I'm sorry I can't give you a better answer than that. But maybe I'll if I've got an idle moment sometime, I'll have a look at some of the Penrose stuff and see if there's anything in there about it.
Yeah, I can't imagine any other universe being as small as a solar system, because if they came into existence like ours, they'd be ever expanding.
Exactly,
and
that's right.
Yeah, they wouldn't be tiny at all. And so I don't think, in the scheme of things, that there'd be too many tiny universes, if any. It reminds me of a science fiction show I saw once about a human astronaut who ended up on this planet and discovered the aliens living there, and he befriended a couple of them and ended up being sort of captured, and he was taken to the town mayor, and he was trying to explain what the universe was all about. And the mayor said, no, there's nothing beyond 500 miles of our planet. That's it. That's as big as it is. So they were very naive. But I thought, that's what popped into my head when I read Jeffrey's question. This is Space Nuts.
What popped into my head? Sorry to interrupt, Andrew.
That's okay.
I think what Jeffrey's talking about is the tinyverse, isn't it? It's the tinyverse.
Yes. Could be, yes. Yeah. Well, to an ant.
Yes.
Anything, a few centimetres from the anthills, probably the extremities of the universe.
It's over the horizon. That's right.
Yeah, exactly. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Okay, let's continue going through our questions. This question, I'm going to laugh at this because it comes from Rosie's husband.
Hi, Fred and Andrew. Thanks for the podcast. It's really great. My wife, Rosie, and I have been listening since about episode 100. Now, in relation to dark matter, I was just wondering if, in relation to gravity's mass, whether the curvature of light, the gravitational lensing that a particular galaxy might produce, could be used to infer its mass also, and whether that, if anyone's done the sums, whether that correlates with the masses derived from angular momentum. That's to say, does the gravitational lensing also support the dark matter gravitational interaction theory? I hope you know what I'm talking about. Thanks very much. Bye.
Thank you, Rosie's husband. I must confess that one confuses me. I'm not quite sure where he's coming from, but I hope you do, Fred.
Yes, and the answers to the questions, to Rosie's husband's questions, are yes, 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 and yes.
Wow.
So
that was easy.
So what he's saying is, if you've got a galaxy, you can infer its mass from the way it's rotating, and that turns out that the mass that we find from that method is much greater than the mass that we can see, and that's why we infer the idea of dark matter. But what he says is, okay, if there's light coming from a more distant galaxy behind it, and it's bent by the gravitational attraction of the galaxy, which is what Einstein's theory says will happen. Does the mass you measure from that tally with the mass that you measure from the rotation of the galaxy? And the answer is yes. And in fact, it's more, it's a richer field of study than that, because we use the gravitational lensing effect of a galaxy to measure the amount of dark matter in the galaxy. But also, you can map the dark matter in a cluster of galaxies. So if you've got, and we've got many, many instances of this through space, you've got a cluster of galaxies. They are gravitationally massive objects, and they distort the space around them. If you've got another cluster of galaxies behind, you see those distant galaxies their light is distorted by the distortion of the cluster, the foreground cluster, the gravitational lensing of it.
Yep.
And you know on average what those distant galaxies are going to look like. And so what you can do is you can say, okay, this galaxy should look like this, but it's been gravitationally lensed by the foreground galaxy. And you can use that to map the distribution of matter in the foreground galaxy. You can actually map where the matter is, and it's not where you see it, and that's because it's dark matter. Most of it is dark matter. One of my colleagues once described galaxies in clusters as now what did he call it? Hills of dark beacons. The galaxies are beacons of light on hills of dark matter. And we know that because you can map the dark matter by this gravitational lensing technique, exactly as Rosie's husband proposes. So he's right on the money with that. The answer is yes, and we use that technique a lot in astronomy.
There you go. Well done, Rosie's husband. Who didn't give us his name. He gave us Rosie's name, but that's okay. Thank you for the question. We've got one more question to wrap up this episode, and this one comes from Cam. Hello, Andrew and Professor Fred. So there's good evidence that Mars had sizable bodies of water some 3 billion years ago. I was trying to imagine what it would be like to experience aquatic leisure activities in a lake or ocean on Mars back then, aside from the hypothermia, I would imagine, Cam. How does water behave on a planet with only 38% of Earth's gravity? How does it flow and splash? What would waves look like, supposing there was an atmosphere and wind to generate them? Well, it's certainly got wind. What would swimming and diving feel like? I'm guessing I'd be more buoyant. Sailing in a boat, what would that be like? Could you do a belly flop from 200 feet and survive? Long-time listener and fan of the podcast, thank you. Cam from the Blue Mountains. Lovely part of the world too, Cam. Although if you swim in the Blue Mountains, you could probably tolerate it on Mars, I imagine.
Yeah. Look, I think the way to imagine this is, it's a great question. What, if we could have been on Mars when it was warm and wet and we threw a rock into the ocean or the lake, what would the water look like? I think it would be similar to what it is here on Earth, but in slow motion, because you're disturbing a water surface and it's under reduced gravity, as Cam says, about a third of the Earth's gravity. So the droplets of water will move more leisurely through space, if I can put it that way. They'll take longer to return back to the surface after they've been thrown up by a splash. So just think of it all as being like on Earth in slow motion. When you're swimming, your buoyancy would probably be the same because the density of water and the density of your body are similar, but the motion with the water itself would be more leisurely. What makes me say that is recalling the way astronauts behaved on the moon, where they walked when they jumped, and some of them did, in slow motion. And there's that famous footage of, can't remember which astronaut it was, I think it was Apollo 12, dropping a hammer and a feather at the same time. They took a leisurely time.
Oh, yeah, Scott. It was, the astronaut, his name was Scott. I can't think of his first name, but yeah. He's the one that wore the Bulliver watch onto the moon because his NASA watch broke.
That's yes, the Bulliver.
That's why I know who it was.
Yes, that's great. So yes. So think of it as splashing around, but in slightly slower motion. I think that would be okay.
Would the splash be bigger, Fred?
Maybe. I'm not sure, actually. You've got a rock that's just displacing the same amount of water. What's
you haven't got as much gravity. So
that's right. So you could probably So you certainly send stuff up higher. That's certainly true. A belly flop from 200 feet. Not sure about that.
I was about to ask. Yeah, I was going to say, would you survive? that's the most important part of the question. Could you survive a belly flop from 200 feet? If you're big enough, probably.
I wouldn't be game to try it, I have to say.
No, I wouldn't either. I would not. I've been reminded of movies these last couple of episodes when people have asked questions. There was I think it was either Mission to Mars or Red Planet. I think it's Red Planet, where they are stranded on the Martian surface, and they're trying to get to where their base was located because of they landed in the wrong place. And they have to spend the night in the open, and then the next morning they need to pee. Now, notwithstanding the fact that they needed to actually open this spacesuit to achieve this, it was noted that when they were peeing, there was much more significant arc in the flow. They even mentioned it.
Right. Yeah, there you go.
Hey, look at the arc in low G.
Yes, the arc will be good. Yeah.
On reflection, how did they actually achieve that with spacesuits on? I'm thinking there was just a little bit of creative license. Thanks, so. Cam. Great questions. And I suppose it draws attention to how water behaves in other places if there was... But, if it's liquid water... it all comes down to the composition of and size of the planet and the gravitational forces thereof. So it could vary from place to place depending on the circumstances. I suppose is the best way to answer it without actually going into detail. That's my thought.
I think that's right too. Yep.
All right, Cam, lovely to hear from you. Thanks for sending your question in. Thanks to Rosie's husband, Jeffrey, and Tobias as well. And thanks for listening for so long. Really appreciate that. Don't forget to send us your questions via our website, spacenutspodcast.com or spacenuts.io. You can do that via the AMA tab at the top where you can send text and audio questions, or the send us your questions on the right-hand side for audio only. But don't forget to tell us who you are or where you're from, like Rosie's husband did. All greatly appreciated. Love getting your questions and working our way through them. Thanks, Fred, as always. It's great fun.
It is. As long as it stays that way, we'll do it again.
Yes, indeed. Fred Watson, astronomer at large, and thanks to Hugh in the studio for fixing all our edits. I think he's got about 200 or 300 of them in this episode to deal with. Good on you, Hugh. And from me, Andrew Dunkley, thanks for your company. Catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.